Hey there, this is the last video for Chapter 6, Section 3. In this video, we're going to be combining some ideas from the last two videos and some ideas from Chapter 4 when we talked about binomial distributions. I know these might seem to run together because they're similar, but if you're keeping good notes on notation and keeping track of the questions you're supposed to be asking for each type of confidence interval problem, you should be in good shape. Also, you're probably preparing for the Chapter 6 quiz and Exam 3. You do have quite a long time for this exam, but do yourself a favor and don't wait till the last minute. You won't be happy with yourself if you get a bad grade because you didn't plan this out. You're not going to be in class the whole week of Thanksgiving, so if you have family stuff happening that whole time, do yourself a favor and plan to do everything outside of that time so that you're covered. Take care of school business before the holiday, or know when you're going to be devoting time to do it after the holiday. Don't let it catch you off guard afterward and all of a sudden you're overwhelmed. Okay, pep talk over. You can do this. Let's get started. Welcome to the lecture video for Chapter 6, Section 3, Confidence Intervals for Population Proportion. In this video, we're going to define what a point estimate for population proportion is, and this is a different type of population parameter, so it should have different objectives when it comes to constructing and interpreting confidence intervals. And we're going to learn how to determine the minimum sample size required when estimating a population proportion. So first, let's review some of the guidelines we used when determining whether something was a binomial probability experiment. For one thing, it had to be a fixed number of trials N, all of which were independent of each other. Next, there are only two possible outcomes, success or failure. We also talked about how the probability of success, or P, was fixed, and so is its opposite, the probability for failure, Q. And finally, how the random variable X counted up the number of successful trials. With binomial probability experiments, we answered questions like this. Rotator cuff surgery has a 90% chance of success. The surgery is performed on 3 patients. Find the probability of surgery being successful on exactly 2 patients. We asked ourselves questions like, what is the value of P in this problem? For this one, P is the probability of successful surgery, which would be 0.90. So how did they get this value? How did we know that the proportion of successes, this population proportion P, was 0.9? First of all, we want to identify this variable. The probability of success in a single trial of a binomial experiment is P, the population proportion. Well, just like we used X bar from a large enough unbiased sample to best represent the population parameter mu, in this case, we also want to start with a point estimate for the population proportion P. The point estimate for this one is called P hat, and it looks like this. A lowercase p with a little caret on top like a hat, hence the name, P hat. Very original, I know, just like X bar. Okay, so this is the population proportion of successes given by the proportion of successes in a sample, and is denoted by P hat equals X, or number of successes, over N, or sample size. This gives us the sample proportion. A proportion means the number of times you see it out of the total number of trials, so this formula makes sense. Then we use the complement rule to find the point estimate for the population proportion of failure, which is called Q hat, which is 1 minus P hat. Okay, let's do an example. In a survey of 540 U.S. adults, 378 said they plan on traveling this summer. Find a point estimate for the population proportion of U.S. adults who plan on traveling this summer. So if we follow the formula, we have the number of successes as the number of adults who plan to travel this summer. So X is 378 and the sample size N equals 540. So the sample proportion is P hat equals X divided by N, or 378 divided by 540, which is 0.70. And we read that as 70%. Now, is it likely that this number is exactly what the true population parameter is? Not really. So we need to add in a confidence cushion in there. So let's talk about building a margin of error like we did before. We're going to create a C confidence interval for the population proportion P by building a margin of error that we can subtract from our point estimate and add to our point estimate. And the formula that we're going to use for our margin of error is here. This looks very similar to other margin of error formulas we've had. Don't let the notation scare you. Those are just the symbols for these new terms, p hat and q hat, which just means the sample proportion for success and the sample proportion for failure. The full equation is multiplying z sub c, which we've seen before, times the square root of the ratio p hat times q hat divided by the sample size. Since we're using z sub c in this situation, you guessed it, you can either use the standard normal table or inverse norm function on your calculator to find those numbers. There's not a special function for this one, it's using z-scores. So the way to say this is that probability that the confidence interval contains p is c, assuming the law of large numbers. That is, that the estimation process is repeated a large number of times. Now there is an extra step here, and it's because we're dealing with binomial distributions. Remember how we had to verify that n times p and n times q were equal to or greater than 5 in order to proceed when we worked with them before? Well, we have a similar condition when working with approximating a population proportion. The two products you need to perform here are n times p hat and n times q hat. If both are greater than or equal to 5, then you can proceed. So let's talk about the steps to take for this process in words and in symbols. It's very similar to the others that we have done. First of all, we need to identify that the confidence interval wanted is for the population proportion. That will separate it from either of the other types of confidence intervals we've worked with before. Next, identify the sample statistics in the problem, like x and n, and identify the confidence level desired, c. Secondly, find the point estimate p hat. Remember, this means x divided by n. After that, you will need to verify that it passes the condition of the two products, n times p hat and n times q hat. Are they both larger than or equal to 5? If so, you may proceed, and it can be approximated by the normal distribution. Your next step is to find the critical value z sub c that corresponds to the given level of confidence c. You can do this with the standard normal table in Appendix B, or use your calculator in the inverse norm function. After that, you'll find your margin of error. You will use this formula for that. You'll need to use the complement formula to find q hat, and then be very careful of parentheses and how you enter the numbers in your calculator. I'll go over an example of that in a little bit. Lastly, find the left and right endpoints by subtracting e from p hat and adding to p hat to get your lower and upper bounds to create your confidence interval. Okay, let's try an example. Use the data in example 1 to construct a 95% confidence interval for the population proportion of U.S. adults who plan on traveling this summer. Remember these data values from that problem. N equals 540, X equals 378, and C equals 0.95. Okay, first of all, it's asking specifically for population proportion, so that tells us we're looking at finding p hat. Next, what data have they given us? Well, we have N equals 540, X equals 378, and C equals 0.95. Great, I think we're good to get started. Next thing we need to do is find p hat, which, if you'll remember, is x over n. So 378 divided by 540 gives us 0.70. We can use the complement rule to say 1 minus 0.7 gives us 0.3, so that is q hat. Now we need to check our products, n times p hat and n times q hat. When we do that, we have 540 times 0.7 and get 378, which is greater than 5, and 540 times 0.3, which is 162, which is greater than 5. So we're good there. You remember what comes next? Next, we use the c value of 0.95 and our calculator function inverse norm, or the table, to find the z sub c value of 0.196. Then we can find our margin of error e using the formula e equals z sub c times the square root of the ratio p hat times q hat divided by n. Pause the video a moment to see how you do that. you should have gotten 0.039. Here's how I would enter this into the calculator. I'd input 1.96, then the multiplication button, then the second button, then the little x squared button, which has the square root above it, then open parentheses, then 0.7, then the multiplication button, then 0.3, then close parentheses, then the division symbol, then 540, then enter. Basically, I put parentheses around my numerator within the square root sign. Okay, so my result was 0.039. Next, all I have to do is find my left and right endpoints by subtracting that number from p hat, which we found earlier to be 0.7. So 0.7 minus 0.039 is 0.661, and then we add it to p hat, or 0.7 plus 0.039 gives us 0.739. So we have an interval of 0.661 to 0.739. And the way we can word our conclusion is, with 95% confidence, you can say that the population proportion of U.S. adults who plan on traveling this summer is between 66.1% and 73.9%. You know, in the real world, when you're reading statistics, they often will write it as stating the point estimate and will say with a 0.04 margin of error, or plus or minus 2.4%, instead of giving you the range. Just a note to watch for and relate to what you've learned. You'll know what they're talking about and how they found it now. Now, we've talked in a previous section about how whenever the confidence level increases, when we go from 90% confidence level to a 95% confidence level, that initially made our z sub c score bigger, which makes our error bigger, and that makes our confidence interval widen. We realized widening the confidence interval was not great because that decreased precision. Remember what our solution to that was? We said finding the right sample size. Well, that is the situation now too. So that's the last thing we're going to go over in this section. Given a C confidence level and a margin error of E, the minimum sample size N needed to estimate P is this formula. N equals P hat times Q hat times the ratio Z sub C divided by E, quantity squared. Now this formula looks hairy, but just like the last one, it's simply derived from the E formula solved for N. I challenge you to pause the video and take a moment to look at the margin of error formula for E and solve it for N to see if you arrive at this formula. I bet you do. Okay, another couple of points about this. If you arrive at a decimal result, you're going to need to round N up to the next whole number. A lot of your figuring is going to be about objects and people, and those can't be figured in parts, so the convention is to round up. Also, this formula assumes you have an estimate for P hat and Q hat. If you do not have a value for P hat to start with, and remember, you can use the complement rule to get Q hat, so you don't necessarily need that to start with. But if you don't have anything for P hat, use P hat equals 0.5 and Q hat equals 0.5. Okay, let's try an example, put all this together. You are running a political campaign and wish to estimate with 95% confidence the proportion of registered voters who will vote for your candidate. Your estimate must be accurate within 3% of the true population. Find the minimum sample size needed when 1, no preliminary estimate is available, and 2, when a preliminary estimate gives P hat equals 0.31. Okay, let's first look at the situation when no Gallup poll has been given. You haven't done any sort of canvassing, and you really don't know what the proportion of people are supporting right now. No preliminary estimate is available. So we know we're looking for a confidence interval for a proportion. We don't have P hat or Q hat, so we're going to have to work with those values that we talked about at 0.5. So what values do we have for the formula for finding the minimum sample size? We need P hat and Q hat, Z sub C, and E. Well, we have C as 0.95, so we can figure out Z sub C on our calculator or with the table to be 1.96. And they actually gave us E because they want it to be accurate within 3% of the true population. So E needs to be 0.03. Now we can do the formula for n. We have 0.5 times 0.5 times 1.96 divided by 0.03 quantity squared. We get about 1067.11. And because it's not a whole number, we round up. And with no preliminary estimate, the minimum sample size should be at least 1,068 voters. Great job. Let's do the second part. This time we have a value for p hat of 0.31. So we use the complement rule to find that q hat is 0.69. Again, they gave us 0.95 as c, and we just found that that means z sub c is 1.96. And we have e the same as before as 0.03. Now we can do the formula for n, and we get about 913.02. Again, since this is not a whole number, we round up to 914. Therefore, the minimum sample size should be at least 914 voters. You'll note you need a larger sample size if no preliminary estimate is available. Okay, that was a quick one. That is the end of this section and this chapter. Good job. Good luck on your quiz and on your Chapter 5 and 6 exam. I'm rooting for you. Talk to you in the next video.